You know that sound an ambulance makes as it speeds past you? That classic neon? We've all heard it. Well, believe it or not, that simple everyday sound holds the key to understanding the sheer vastness of our universe and even how we can literally look back in time. So, how on earth does that work? Well, it all kicks off with one simple question.
Right, this is the one. We've all experienced this. But the physics hiding behind that sound, well, that's what led astronomers to one of the most profound, mind-blowing discoveries in all of human history. Okay, so let's really dig into what's happening with that siren song. Now, this phenomenon has a pretty famous name, one you've probably heard before, but the idea behind it, it's actually surprisingly simple when you break it down. It's called the Doppler effect. And here's the absolute key to understanding it. The shift in sound is only apparent. The siren itself isn't actually changing its tune at all. It's your perception of it that's changing. And it all comes down to one thing. Is it moving towards you or away from you? Now, this applies to pretty much any kind of wave, but let's stick with sound for just a minute. So, picture this. It's all about how those sound waves are hitting your eardrums. As that siren is racing towards you, the sound waves it's pumping out get all smushed together in front of it. That means more waves are hitting your ear every second. That's a higher frequency, which our brains interpret as a higher pitch. Then, the second it passes you and starts moving away, those same waves get stretched out behind it. Fewer waves hit your ear per second, the frequency drops, and you get that classic low pitch. Simple as that. Okay, so that's sound waves. Pretty straightforward, right? But here is where things get truly cosmic. Because that exact same principle, it doesn't just work for the sound from a siren. It also works for the light coming from a distant star. The big idea here is that light, just like sound, travels in waves. Now, sure, they're a different type of wave, electromagnetic waves, but what matters is they still have a frequency. And that frequency can be compressed or stretched by motion, which gives us a kind of cosmic Doppler effect. So here's how that plays out across the universe. If a galaxy is moving towards us, its light waves get compressed or smushed together. This pushes them toward the shorter, higher energy end of the light spectrum. That's the blue and violet part. We call this a blue shift. And you guessed it, if a galaxy is moving away from us, its light waves get stretched out. This shifts them toward the longer, lower energy red end of the spectrum. And that, my friends, is the famous redshift. Now, this whole idea of redshift wasn't just some neat little physics trick. Oh no! Back in the 1920s, an astronomer you've probably heard of, Edwin Hubble, took this concept and used it to completely, utterly revolutionize our understanding of the entire universe. Hubble found something that was just mind-bending. The redshift he was seeing from all these distant galaxies, it wasn't just because they were flying away from us through space. No, it was because the fabric of space itself was expanding, like a balloon being blown up. And as space expanded, it stretched the light waves traveling through it over billions of years. This is what we call cosmological redshift. And then Hubble uncovered this critical clue, a clear pattern in his data. As NASA science puts it so well, he found that the farther away a galaxy is, the more prominent its redshift is. In other words, the most distant galaxies were also the ones moving away from us the fastest. Whoa. And this is it. This relationship became known as Hubble's law, and it's basically the ultimate cosmic yardstick. Think about that. If we can measure how much a galaxy's light is redshifted, we can figure out how far away it is and how fast it's speeding away. This was the first solid, concrete proof that our universe is expanding. So redshift became our key to unlocking the cosmos. But of course, it's never quite that simple, is it? As astronomers got better and better at measuring it, they realized the story was a little more complicated. The redshift they were seeing wasn't just from one thing. It was a mix of a few different effects all piled on top of each other. Yeah, it turns out astronomers have to deal with three main types. First, you've got the big one, the cosmological redshift from space itself expanding. Then, number two, you have the classic Doppler redshift. That's just a galaxy's own individual motion through space, kind of like a car changing lanes on a highway that's also stretching out. And finally, get this, there's even gravitational redshift. That's where light actually loses energy and shifts red just by trying to escape the immense gravity of something massive, like a galaxy cluster. So trying to untangle all these different effects is a massive challenge. The holy grail for physicists is to find a single, unified treatment, one elegant theory that can explain any shift in frequency. It wouldn't matter if it's the sound from that ambulance we started with,
the light from a star in our own backyard, or the stretched out light from the edge of the universe. One theory to rule them all. Now, actually building that unified theory is incredibly complex, but it boils down to nailing a few core ideas. It's about perfectly tracking light's path through space-time, figuring out exactly how our own motion as the observer changes what we see, and then finding the math to separate all those different effects from each other. It's like a roadmap for physicists to get to the complete picture.
Okay, and all of this science builds to what is for me the most incredible consequence of all. Because Redshift doesn't just tell us how far away something is or how fast it's moving, it is, quite literally, a time machine. It gives us a window into the deep, deep past. Just stop and think about this. Light doesn't travel instantly. You know, the light from our own sun takes 8 minutes to get here. The light from the next closest star takes 4 years. So when we look at a galaxy that is billions of light years away, we are seeing light that left that galaxy billions of years ago. The farther out we look, which means the higher the redshift, the farther back in time we are seeing. Let's take a real-world example, a galaxy called GNZ11. Astronomers measured its redshift value, they call it Z for short, at an absolutely incredible 11.1. Now, that number, that isn't just about a jaw-dropping distance. It represents an unbelievable journey through time. And this timeline really puts it all into perspective. The light we're seeing today from that galaxy, GNZ11, actually left it 13.4 billion years ago. That's just a few 100 million years after the Big Bang itself. We are literally looking at a baby galaxy in an infant universe. And it all comes back to that simple thing, that change in pitch from a passing siren. That's what lets us watch cosmic history unfold before our very eyes. So all of this leaves us with one heck of a question. With every powerful new telescope we launch, like the James Webb Space Telescope, we're able to see things with even higher and higher redshifts. We're pushing our gaze closer and closer to the very beginning of time itself. So we have to wonder, what secrets are still hiding in that ancient light? What are we going to see next?